So far, what we've been doing is finding the derivative at a point, which means we've been plugging in a value for x to equal. What we're going to look at in this video is what if we wanted a general derivative function. So the idea that we could find the slope of the tangent line or instantaneous rate of change for any value of x. So let's let f of x equals 5x squared minus 3x plus 1, and we want to find the derivative function for f. So our process is going to be the same, but what's going to change is we will not have a numerical value for x. Now we're going to leave that as x and evaluate around it. So what that will look like is if we're looking for a general derivative function, so f prime of x, we would be taking the limit as h approaches 0 of f of x plus h. So in this case, what we'll be doing is plugging in x plus h for our first evaluation. So 5 times x plus h squared minus 3 times x plus h plus 1. And then we're going to subtract f of x. So with that, we're just going to copy our entire function, 5x squared minus 3x plus 1, all divided by h. And we're going to go through the same process where we're going to simplify until we can cancel out h, which should occur with these, so that we can plug in h equals 0. Now with these, we are going to have multiple variables hanging out, so it's just very important to go slow and steady with these to make sure everything works out correctly. So let's start simplifying. So limit as h approaches 0. So we're going to have 5 times, and then x plus h squared is going to be an x squared plus 2xh plus h squared. Again, if it helps, and because we'll be doing this quite a bit with these, is x plus h squared is our same thing as x plus h times x plus h, and foiling. And then I'll distribute the negative 3, so minus 3x minus 3h, and then a plus 1. And just to show you what I just simplified, this was all in the first set of parentheses. And then second set of parentheses, I'm just going to distribute the negative. So I'm going to have minus 5x squared plus 3x minus 1. And that's where parentheses are so important, and it's because you need to distribute the negative. That's a very common mistake here. All the calculus can be going correctly, but distributing the negative is often a tricky spot. So make sure you carry that out. That's why I like showing these bright blue parentheses to show how it's all coming through. All right, all divided by h. Okay, we're getting there, and we'll get some cancellations coming through. So let's see, distributing the 5, so 5x squared plus 10xh plus 5h squared. And then we'll have a minus 3x minus 3h plus 1 minus 5x squared plus 3x minus 1 all over h. And this is where some things should be starting to turn into 0. So like we have positive 5x squared and negative 5x squared. So those will turn into 0. Minus 3x plus 3x, that'll turn into 0. Plus 1 minus 1, that'll turn into 0. So when we carry this out, we should be left with all terms that involve h, because then we'll have a nice cancellation with h across each term. So cancel out an h, we'll have one h left over, cancel out an h. So we're taking the limit as h approaches 0, and with all those zeros that came through, canceling out an h, we're left with a 10x plus 5h minus 3. And if we plug in h equals 0, we're going to be left with 10x minus 3. So what we have here is a derivative function, f prime of x, is equal to 10x minus 3 that will be graphing the derivative for all of our values for x. So what this does, and we can't really graph it on the same line here because we'd be down here, well, it would be even steeper. But the idea is that we'd be seeing these negative slopes until we reach this point where we'd have a slope of 0, and then we'd have these positive slopes, and that's coming through. Like if we plug in 0 for x here, we'd see -3. That's the slope of our line right here, is a -3. If we plug in, what's another point? If we plug in a +1, 10 minus 3 is 7. That's the slope right here. We have a +7 slope of a tangent line. So we can look at different values for x and see what the slope of the tangent line is doing, what's the instantaneous rate of change doing, by plugging into this function right here as it relates to this parabola function. Find the derivative of f at 1. Use this to write the equation of the line of the tangent line to f at 1. So now we could go through how we did this originally. So finding f prime of 1, what we did before was that limit as h approaches 0 of f of 1 plus h minus f of 1 over h. We can absolutely go that route, but it's a little redundant based on the work that we just did. We just found our general derivative function. So instead of that, what I can do is, if I'm looking for f prime of 1, well, I know f prime of x is 10x minus 3. So what I would do is just plug in 1 into that derivative function. So 10 minus 3 is 7. So there's our slope of the tangent line at 1. And then I would be going y equals 7x plus b. We're looking at the coordinate 1, and I can see from the graph it's the coordinate 1, 3. So plug in 3, plug in 1, solve for b. 3 minus 7 for a -4. So we have y equals 7x minus 4 would be our equation of the tangent line at x equals 1. So if I graph the tangent line, that would be the line 7x minus 4. Find where the derivative is 0. And I kind of already mentioned, I have an idea that it's right. Let me use a different color there, that it is right here, because that's where we would have a flat tangent line. But let's prove it. Having something that's between 0 and 1/2 come through in our calculation. So what I'm doing here is I'm looking for where is f prime of x equal to 0. So with that, I'm really solving 0 equals our function 10x minus 3. Add 3 to both sides. Divide by 10. X equals 3/10 is where we have a derivative of 0, and that's what I'm seeing right here. This is a value of 3/10 is giving us a derivative of 0 because that's our turning point. Okay, so there's an example with a quadratic function of how we can find that derivative function and then use it to answer various questions. Now let's take a look at a rational function. Well, finding the first derivative here for our function g, given that it's a rational function. So we're looking for the function g prime of t. And what we're going to do is take the limit as h approaches 0 of g of t plus h minus g of t all over h. So the limit as h approaches 0, and we're going to look at t plus h divided by t plus h plus 3. So there's our first plug-in, minus just our function t over t plus 3. All over h. Nothing to plug in the denominator, that'll just stay h. Okay, so in our last videos we talked about with rational functions using our least common denominator to simplify. So in this case, my least common denominator is going to be the multiplication of t plus 3 times t plus h plus 3. So just getting a little messier, but it's still going to work in the same way. So what we're doing here is I would be multiplying with a t plus 3 times a t plus h plus 3. Same thing here, t plus 3 times t plus h plus 3. And then same thing down here, t plus 3, t plus h plus 3. So again, in the numerator, it's because it's distributing that it goes to two places. It's distributing across that subtraction, but really is that we're multiplying the numerator by that least common denominator, multiplying the denominator by the same least common denominator, so that really we're just multiplying by a version of 1. So when we do this, we should get some nice cancellations happening. So with that first one, the t plus h plus 3's will cancel. Here, the t plus 3's will cancel. And then I'm going to leave that denominator factored because I'm going to look for some more cancellations later on. So we're taking the limit as h approaches 0. I am going to multiply out the numerator. So I have a t plus h times t plus 3. So I'm going to FOIL so that I have t squared plus 3t plus ht plus 3h. And then I have a minus t, and I'm going to distribute that through t plus h plus 3. So I'm going to have a negative t squared minus ht minus 3t, all divided by h times a t plus 3 times a t plus h plus 3. So I still can't plug in h equals 0, mostly because of this h right here hanging out, which would turn the whole denominator into 0. Okay, let's look for some cancellations here. So t squared minus t squared, that'll turn into a 0. 3t minus 3t, that'll turn into a 0. ht minus ht, that'll turn into a 0. So all I have left over is this plus 3h. And that gives us a nice cancellation of the h's, so that we are just looking at the limit as h approaches 0 of 3 divided by t plus 3 times t plus h plus 3. And if we plug in h equals 0, we have our function 3 over t plus 3 times t plus 3. In fact, let's go ahead and just write that as t plus 3 squared. So there is our derivative function. Let's even write that to the side. So g prime of t, our first derivative of g of t, is 3 over t plus 3 squared. So now we can evaluate the derivative for any value of t. So find g prime of -6 and use this to write the equation of the tangent line at -6. So we're looking at this spot right here and finding the equation of our tangent line. Something like that. And in fact, if I continue this on, I could get an idea of where we'd be hitting on the y-axis. So let's go from there. So g prime of -6, now we can just plug into our derivative function. So 3 over -6 plus 3 squared. So a 3 over 9, so we are getting a 1/3 for a slope. And then plugging in our coordinates, so -6, 2. So output of 2, 1/3 times a -6 plus b. So 2 equals -2 plus b, so we're getting a 4 out. So y is equal to 1/3 x plus 4. So I was a little off there with drawing my tangent line, but now I could draw it exactly here. So we're at 4, and then a slope of 1/3 would look something like this, which looks really good to me. So there we go. So there's our property for rational functions. You want to use that least common denominator. Let's go through some more scenarios here. So what I'm trying to do is just get us all those algebra rules that we might need for finding these derivative functions. So we have a radical function, root x plus 4, and what we're going to do is find our first derivative formula for our function. So this is q, so we're looking at q prime of x. So we're going to look at the limit as h approaches 0, q of x plus h minus q of x all over x plus h equals, so we're going to have the square root of x plus h plus 4 minus root x plus 4. So I have my first function minus the second function all over h, and I left out my limit notation, so for consistency I'm just going to squeeze that in here because it is important that we're still evaluating that limit as h approaches 0. Okay, so something we're going to bring in here, which we talked about previously, is our multiplying by the conjugate. So what I'm going to do is multiply this entire numerator and the denominator as well by the conjugate. So what we do is we keep the first term and second term the same. So I'm going to have root x plus h plus 4 and root x plus 4. But now instead of subtraction between them, what makes it the conjugate is putting addition between them. So it lets us use the difference of squares here. Then whatever I multiply the numerator by, I also have to multiply the denominator by. Okay, so let's see how this works out. So if we start foiling up there, what should end up happening is we would lose that middle term, and what we would end up with in shorthand would be that first term, so that root x plus h plus 4, that would be squared. We would be multiplying that with itself, and then minus, and we would lose those middle terms, and all we'd have left over is that root x plus 4 also squared. So this is kind of our reverse difference of squares for factoring. It's kind of multiplying it out, has us end up with the difference of squares. And then the denominator, I'm going to have root, and then just that x plus h plus 4 plus root x plus 4. So how this will simplify is we get to get rid of those radicals. So it'll be an x plus h plus 4 minus x plus 4 in parentheses. So distribute the negative minus x minus 4 all over all that stuff. Okay, so looking for our cancellations, we have x minus x, 4 minus 4. So all we have is an h left over in the numerator. So we'll have a nice cancellation to leave us with a 1 in the numerator. So we're looking at the limit as h approaches 0 of 1 over that root x plus h plus 4 plus root x plus 4, which if we plug in 0, we'll just have 1 over root x plus 4 plus root x plus 4. So really we have 2 of those root x plus 4s. And that'll be our derivative function. So 1 over 2 times root x plus 4. Let's use our derivative function to state the slope of the line tangent to Q at 0. So we're looking at 0 here, and if I just kind of sketch, ooh, that was a little too steep. If I sketch the tangent line, maybe it would look something like this. Ish, kind of. Let's get the exact value. So we're looking at Q prime of 0, which would be 1 over 2 times root 0 plus 4, which would be a 1/4. So I would have a slope of 1/4, and then I can see the y-intercept is at that value of 2. So I have a slope of 1 over 4. Oh, that's pretty close there. But just to get it more exact, having the slope of 1 over 4 would look like this. That looks like a good tangent line right there. Okay, so those are the main types of functions we'll be working with. We'll of course see others as well, but are radical, rational, and quadratic. Okay, one last example here to finish up this video before we go on to the next one. So let's just say, given a graph where we're not given the function and we want to talk about what the derivative is doing. So when is the particle moving to the right? So what we're seeing is a distance. So you can see this distance is increasing from 0 to 1. And that's going to be where it's moving to the right. So a particle starts by moving to the right along a horizontal line. So it's on a horizontal line moving further and further away until it's 4 meters away. Then it's not moving at all. It just stays put for a little bit. And then it comes back. So that distance away starts decreasing. So it comes back to us. Then it stays put for a bit. And then it starts traveling away from us. So it's how the distance is increasing and decreasing, or if it's staying the same. So when is the particle moving to the right? Well, it starts moving to the right at 0, and then it stops moving to the right after 1 second. And then it starts moving to the right at 6 seconds. And then let's assume it stops at 8. We'll end there since there's no arrow there. Was it moving to the left? That's where it would be decreasing in distance, and that happens from t = 3 to t = 5. So that occurs from 3 to 5. So what we have is this is where it's moving to the right, to the right, to the left, and this is where it's going to stay put. So that's where it's just staying put at those flat lines. So what we're really talking about is the slopes here and what the slopes are doing. Is it increasing, decreasing, or is it 0? So the particle is standing still from 1 to 3, and then again from 5 to 6. Okay, so let's say we wanted to draw the velocity function. So what's nice about these is that this is all linear. So the slope is staying the same. So for this region 0 to 1, the slope is staying put, and we can see this slope of 4. So it's moving 4 meters per second from 0 to 1. So if I wanted to draw that at 0 seconds, it's going 4 meters per second, and it's traveling that same velocity until I reach 1 second. Then it stays put, which would be a velocity of 0, which is our slope right there. We have a slope of 0. So actually, let's use all open circles here, just for the sake of not by graphing a function. We need to pass that vertical line test. So from 1 to 3, we're down here at a velocity of 0, where it's not moving to the right, it's not moving to the left, it's just staying still. Then from 3 to 5, so this is where we are decreasing, so we're going backwards, and we're going, this will be a little tricky because it's a slope of negative, and I didn't have enough space in my graph, so this will be a slope of -1/2, so -1/2. So from 3 to 5, I'm actually below the graph here. So just for the sake of having our graph complete, I'm down here at -1/2. And then we're back to staying still from 5 to 6. So no velocity there. And then from 6 to 8, looks like a slope of +1. So we're going to be traveling at 1 meter per second across there. So the velocities stay the same because the rate of change is staying the same with it being linear. So that's how we're getting those graphs out. But it's like having this velocity of 4 meters per second, velocity of 0, velocity of -1/2, velocity of 0, velocity of 1. So velocity is being represented as negative when we're moving in a backwards direction, but then positive when we're moving in a forwards direction, in this case moving to the right.